Yeah, I think we are live. Hello, guys. Thank you, everyone, for joining the session and showing the consistent interest in electric vehicle webinar series. So, as you are aware that we have been doing this webinar series for students, where the student can learn the hands-on technology from the expert who are really doing this and building this in the ecosystem. So we are keep inviting the experts who can guide you on the newer technology and how you can fit into the EV ecosystem. So today we have Mr. Bhavesh Kumar from Simulia, Dassault System India with us. So first of all, I want to say a heartfelt thank to Mr. Bhavesh that he agreed to share his time for the student community to learn EV industry. Thank you, Bhavesh. Thank you for coming and agreeing for the webinar first.
It's my pleasure. Thank you, Vijay, for inviting. Really excited to be a part of this webinar series today, and I'm sure that we would have a very interactive discussion on simulation for electric vehicles.
Sure. So, Bhavesh, I want to start with a just quick background how the electric vehicles industry has shaped, or in fact, the how vehicle industry has shaped, because the ICs are like now a aged backdated technology, because now we are seeing the connected electric and autonomous and shared fleet, which are going mainstream in many countries. So, how do you see overall transformation in the mobility?
I would say that even in India, we are seeing electric vehicles in general, pick up quite a lot, especially in the area of public transportation. We have already been seeing electric vehicles come into the play. The government of India also, right from the past, has been looking at initiatives such as FAME to increase the adoption of electric vehicles. Of course, there are always going to be challenges, whether we look at it from the point of view of charging infrastructure, battery technology, and so on. And I feel that this is where the role of simulation becomes very important. And we've also seen in the last few years startups emerge in the area of electric vehicles, more so than any other domain, I would say. And maybe during the course of my talk, I could talk about how the startups also are really looking at these types of challenges. But vehicle electrification is here to stay. I think it will only become more and more common in the coming months and years.
Sure. So, guys, as a quick background about Bhavesh, so that you guys are aware that how Bhavesh would be sharing his experience. So, Bhavesh is has been working quite a lot in automotive industry, and he's the director for the Simulia with the Dassault system in India. He has also been managing the business growth and customer engagement for the Simulia India Center for Excellence to assist customer across the Asia Pacific and serve them. Uh, Bhavesh has also done the master's in mechanical engineering from State University of New York and has a bachelor's in mechanical engineering from NIT Trichy. So that was a quick background of the Bhavesh. Yeah, Bhavesh, before you jump to the PPT, I want to like get more into the simulation and its application in the EV industry. So if we see the COVID-19 has impacted the entire world, and now people are preferring more uh, to prototype their products before rolling out, or even to make the prototypes of those products. So how do you see entire landscape of the simulation and modeling changing the entire industry?
I would say, Vijay, that simulation will only become more important in the post-COVID scenario. And coming from Simulia, which is one of the most well-known brands in the simulation industry, we've also been looking at what role simulation is going to play in the near future. And a lot of things are becoming the norm. Like, for example, work from home is becoming a norm. We are looking at factories opening up, but with the constraint of physical distancing happening as well. And there are times where, therefore, testing and prototyping, what used to happen earlier, could become a little more difficult. That is first thing. The second thing is that a lot of companies would really drive towards a cost reduction initiative and look at more digital transformation, whether it is in the adoption of, let us say, a collaborative platform or looking at cloud technology and so on. And all of this makes simulation, sort of easy to adopt because simulation is inherently digital. And what I therefore foresee is a more aggressive adoption of simulation in the post-COVID scenario. In the past, simulation technology was, there were always concerns in terms of accuracy, in terms of turnaround times, and so on. But I would say that over the past decade, a couple of decades or so, there have been tremendous advancements in the simulation technology, both from a software perspective, like algorithms, as well as the hardware perspective. We have very fast CPUs and GPUs, which are making it possible to run even the most complex problems within a very reasonable time frame. So I think this is a good time for simulation to be in. We see it as the role of simulation we see as positively increasing in the post-COVID world.
Definitely, and companies now need to adapt to more software products so that they can also reduce their costs and resources in prototyping the newer products and venturing into the newer market.
Yeah.
And definitely, simulation is going to add a huge value over there. So, with that, Bhavesh, I extend the stage to you uh, for the presentation about the simulation and how it can help our engineers who are looking to enter into the EV.
Thank you, Vijay, for this opportunity. Once again, I'm really excited to be a part of this masterclass webinar series today. I hope you could see my screen.
Yeah, we can see your screen, Bhavesh.
Okay. So my plan today is to keep my part of the session short, but at the same time to provide an overview of how simulation works on vehicle electrification. I am hoping that we can have a more interactive discussion towards the end. Now, as you all know, simulation as a technology has been around for decades. It's not a new technology. Even commercial applications of simulation go as far back as early 70s. Uh, but what value does simulation hold for vehicle electrification? And that is going to be the theme of my talk. Now, before I get into that, what I would like to do is to help you understand the value of simulation in the automotive industry itself. Automotive industry is about a century old. The use of simulation started, I would say, about 3 decades back in the early 70s or late 70s. And what I will do is to maybe start with a video. This is from Royal Enfield. Royal Enfield. It's a premium motorcycle brand, a company with a legacy of excellence for decades. And you can hear from Royal Enfield themselves, how they use simulation technology today.
So Royal Enfield is the world's oldest continuously in production motorcycle manufacturer with a rich heritage.
So for me, Royal Enfield stands not only as a motorcycle company, it's more like a motorcycle culture.
Obviously, in a modern motorcycle, we have all of the requirements that every motorcycle that is made has to have. So what we're trying to do is to use simulation tools so that it gives our designers a much better idea of the trade-offs and what they have to understand, how the design is working, what things are really important, what things are not so important. Royal Enfield is really famous, particularly in India, for the sound of the motorcycle. So people, when they are riding or when they are in the street, they can hear the sound of the motorcycle and they go, that's Royal Enfield.
There are ribs inside the covers. We developed a methodology where it's basically called a sizing optimization. That basically shows us how the ribs should be aligned based on a frequency based sizing optimization.
Key to a good engine durability, I have found from previous experience, is to make sure that the crankshaft has a very good durability.
Earlier, we used to assess the durability individually, like we assess the durability of con rod, or we assess the durability of crankshaft separately. But now we have a multi-body dynamics model, including the flexible bodies with piston, con rod, and the crankshaft.
A lot of people for high performance motorcycles would use a forged piston because of the perceived strength benefits. But the problem with that is when you forge a piston, you end up using more material, so the pistons are actually heavier. So what we decided for Royal Enfield was if we use a cast piston, we can actually make things thinner, but we have to do a lot more analysis to make sure that the piston shape is correct.
We divide the piston into many number of regions with different heat transfer coefficients and sink temperatures and the flux coming onto it. We got a pretty good correlation.
Dassault system simulation gives us the high quality of the answers that we're looking for. There's no other system really that can provide the quality and the assurance of the answers.
So that was from Royal Enfield, where they are talking about why they use simulation. And if someone asks us why simulation, our answer is, well, simulation reduces tests and prototypes. In the past, people would say that everyone believes in test results except the test engineer, and no one believes in simulation results except the simulation analyst. Nowadays, you would not hear this because simulation is an accepted technology pretty much across industries, not just the automotive industry, but any industry that you take. Today, if you're picking up a shampoo bottle, chances are that it would be designed using simulation technology. It is everywhere. And the value of simulation goes much beyond reducing tests. We use simulation to understand product performance, to explore design alternatives. You could see the head of CAE in Royal Enfield talking about using cast pistons instead of forged pistons. And he mentioned that this is going to involve more number of simulations, more number of validations to be done. And this is why they ended up using simulation, right? So simulation helps us in exploring those design alternatives to manage complexities because products are becoming increasingly complex. The phone that we hold in our hands today is more powerful than the computers that were around maybe 10, 15 years back, right? So complexity is becoming increasing, and also to instill confidence in the end users. So if I or you or a user of a product, we need to feel confidence that that product is not going to fail. And again, this is where simulation comes into picture. So ultimately, all of this helps in reducing costs for the companies, reducing the time that it takes to market the product, managing risks and failures. Well, I would say mitigating failures as well as managing risks, right? And we just talked about the role of simulation in the post-COVID scenario. And you could imagine the value of simulation will increase considerably because companies would want to reduce costs but still innovate, because employees may be asked to work from home and still produce ideas and results, and because business must go on, and simulation is rightly placed to take over now. With that, let me move on to the automotive industry. And we know that there are global trends like electric, connected, and shared mobility, new customer experience because we as customers always demand new things from our vehicles, quality, costs, and regulations, and as mass production to mass customization. Now, these are global trends, but if we look at the trends in India, these are no different. The BS6 emission norm silently took over on the 1st of April when we had our first lockdown. We also have expectations in terms of quality, comfort, and fuel efficiency from our cars. Safety regulations such as crash standards are coming soon. And of course, vehicle electrification, which will be the focus of our talk today. So the first question is, how are electric vehicles different? Yes, there is an electric part which introduces new requirements, such as what should be the battery performance, or how the electric drive and the electric motors should be designed and assembled, right? But how even the regular assemblies in the vehicle undergo a change with electrification. The chassis, for example, has to be modified to accommodate the battery modules. The body has to be designed so that it is lightweight and it could offset the weight of the batteries. And the HVAC system, for example, should be made more efficient. So overall, what you are seeing is that it may look similar on the outside, but there are a lot of very specific requirements that electric vehicles demand. For some of these, the traditional simulation technology can be reused or applied, such as for vehicle dynamics or chassis durability. But what I'm going to do in the next 15-20 minutes or so is to really focus on two very broad aspects where simulation becomes critical. One is battery modeling and one is electric drives. And using these two, we will see how simulation is evolving towards a more multi-scale, multi-physics, and a systems engineering approach. Now, you may ask, what is this multi-scale and multi-physics, and why do we need to really focus on that? So consider an electric vehicle. Ideally, the simulation for electric vehicles would start at the level of batteries. And what are batteries made of? They are made of materials, which means that you are looking at materials, then from there you would want to move towards the level of cells, from cells to battery packs, and then all the way to the full vehicle. And each of this represents a scale, okay? And at each scale, we have to use a different technology. Now, how do you combine chemistry at the material level with structures at the cell level? And we have techniques to do that. They are called as scale bridging techniques. We will not get into that, but if you're interested, we can discuss towards the end. So what happens in real world is that if you take a battery, the simulation that you want to do on the battery ultimately depends on the requirements. And what are those requirements? We want the batteries to be affordable, long range, fast charging, and of course safe. It shouldn't catch fire during a mishap or an accident, right? The requirements translate to specifications. Cost to be reduced or a target cost that we want, energy density to be increased, lifespan to be extended, safety to be assured, and so on. And these specifications translate to a series of simulation workflows, such as battery modeling, thermal management, aging prediction, battery integrity, and energy consumption. In fact, this is what is called as a systems approach. In a systems approach, you start with requirements, and these requirements ultimately translate into a series of simulation workflows at different scales. Now, if you're into battery research, which some of the companies are doing, then you would typically start from the chemistry. And chemistry is molecular level modeling in 3D. And the results of this analysis, chemical modeling, are then used to perform further analysis on battery cells and battery packs across different disciplines, such as structural, thermal, and electrical. And finally, what we do is we combine all of this to get a full vehicle performance, right? And we call simulation that is performed at each level or each scale as a workflow. So there are workflows for battery materials design, there are workflows for battery management system, there are workflows for battery systems modeling, and so on. And each of these workflow relies on a different simulation technology. Some use finite element analysis, some use computational fluid dynamics, some use system modeling approaches, which could be more 1D. What you're seeing here as battery system modeling, for example, is a more 1D logical and physical modeling that we have. But ultimately, all of these need to work together in sync so that there is a single model, what we call as a single source of truth, and there is no confusion in terms of who is doing what. And in order to do this, what we need is a platform where different experts can collaborate with each other. And I'll talk about that in a short while, right? So we covered batteries very briefly, and we looked at the multi-scale part in batteries, going from chemistry to cells to packages to the level of full vehicle, right? Let me now switch to electric drives, where I'll talk about the multi-physics part, okay? An electric drive requires validation across different disciplines. It should be durable, it should be efficient, it should be less noisy but not too silent, it should be long lasting, it should also be cost effective, and so on. So what is happening is that these are essentially the requirements. Now these requirements translate to electromagnetic performance, thermal management, lubrication, durability, and so on. And further, all of these at some point should be integrated with battery engineering that we just saw and power electronics. So what I will do instead of going through what each of these simulation workflows does, is to show you a short video which will tell you how all of these come together on a single model, and why it makes sense to have a single model to drive our multiphysics requirements. Okay, so here is a video that shows you how electric drive works.
Change with electric, autonomous, and connected mobility. Electric drive systems play a key role in battery electric vehicles. The primary challenge in electric drive engineering is achieving a high power density. This means packing high power in a small space that must contain the electric machine, a gearbox, the housing, and often the power electronics unit, integrated or closely attached, all at a reasonable cost. These electric drive systems are complex, and their performance needs to be optimized across multiple competing disciplines, including electromagnetic performance, thermal management, gearbox lubrication, noise and vibration, durability, strength, and stiffness. Achieving the highest possible power density requires an optimal electromagnetic design. Performance is directly related to the overall driving experience and efficiency of the vehicle. Dassault Systèmes electromagnetic solutions allow engineers to analyze electric machine performance, efficiency, dynamic forces, torque, and thermal losses in order to drive the design of the electric machine. The high power output achieved through electromagnetic design generates significant heat. Dissipating this heat is necessary to maximize performance and lifespan, and avoid thermal hotspots and demagnetization. The direct link between the parametric CAD model and the fluid dynamic simulation allows engineers to quickly assess the core temperatures and pressure drops in the cooling system. Engineers are also able to update and improve the design through design space exploration and optimization techniques. The electric machine drives a gearbox, and the high rotational speeds make lubrication critical to system efficiency and lifetime. Multi-phase simulations can help minimize the size of the electric drive by optimizing the oil volume necessary to properly lubricate the gearbox moving parts. Gearbox performance can be improved by minimizing the mechanical losses induced by the lubricating oil. The electric machine and gearbox are enclosed in a housing, which must be modeled as a coupled system in a noise and vibration simulation. Simulating and predicting noise and vibration sources and paths, both structure-borne and airborne, is critical to improve overall cabin comfort and component durability. The end design of an electric drive system is the result of compromise between its performance and design requirements, such as cost, allowable design space, and manufacturing constraints. Dassault Systèmes' tightly integrated CAD CAE solutions help teams reduce engineering cycle times by allowing fast updates of designs across multiple disciplines. Furthermore, design parameters can be optimized across multiple engineering disciplines in a fully automated workflow to deliver a better performing end product. Dependencies between vehicle subsystems have increased significantly in electric vehicles, driving the increased need for a model-based systems engineering approach. 3D Experience allows the direct integration of systems engineering, requirements management, and simulation results, which streamlines the engineering design process, allowing you to optimize performance and efficiency simultaneously across multiple disciplines. Manage complexity with a model-based systems engineering approach based on a single source of truth on the 3D Experience platform. deliver higher quality products with faster time to market. Simulation powers innovation.
So, so I'm just stopping the slide for a moment. So what you saw, is what are the different simulation workflows that an electric drive itself has to go through. So you looked at how this is all multi-physics, but at the same time, you would also have seen the need for doing what is called as multidisciplinary optimization, and looking at a model-based systems engineering approach. So the last one is something that I would talk very briefly about in a couple of minutes. The other thing is something that you would also notice in the current slide is if you are used to looking at simulation, like these colorful contours of stresses and displacements and things like that. Today, the simulation itself is shown in very highly realistic rendering. So this not only makes it sometimes easier for us to understand, but it also looks nice. So that is why I wanted to share, how simulation itself is used in electric drives, because it gives you an idea of what are the different technologies that gets into validating the performance of an electric drive. So with that, what I will do is I will come to the last portion of electric vehicles, which is the full vehicle integration. So we talked about batteries, we talked about electric drives, but at the same time, we now also need to look at the full vehicle integration. Why? Because this is the part that the driver, the passengers, the consumer would be looking at. If I were to buy an electric vehicle, I would ask these questions myself. Is it a fun car to drive and handle? Is it safe in the case of accidents? Will it be comfortable to drive it under, say, scorching sun like we are having in Chennai right now? So what you are seeing here are three different videos. One is on vehicle dynamics, which helps us to understand the ride and handling characteristics of the full vehicle. One is on crash worthiness, which is obviously related to safety requirements. And the third video that you see is thermal management, which means that if you're driving on the road, hot summer noon, and you switched on your AC or you parked your vehicle somewhere, how long does it take for the vehicle to become hot? So, these types of things become critical because ultimately they would impact battery performance and battery life, which is something that we would obviously like to extend. Right now, one thing that I want to also mention is how does all of this impact you and me, like say expert engineers. So I understand that many of you are in your final year of engineering. I am sure and I hope that some of you would get into the area of simulation or related technologies, and you will be working in different disciplines: systems engineer, mechanical engineer, and so on. Now, how does a systems engineer, a mechanical engineer, and an electrical engineer work together in, say, a real corporate world? How do they exchange information without getting confused? And as I said earlier, this is where a collaborative platform helps. Collaborative platform, what you would have seen as the 3D experience platform in the video, ensures that different experts can work with different technologies seamlessly across the product lifecycle, right from the concept level to initial design, to detailed design, to validation and verification, to manufacturing, and sometimes even to look at the maintenance parts of it. And this actually forms the basis of model-based systems engineering, going all the way from requirements to what here you see as fit, form, and function. Now, I want to highlight very, very briefly two other aspects related to electric vehicles, which is connected and autonomous. The first one, what you're seeing here, is connected vehicles, which is more about antenna design and performance, vehicle-to-vehicle communication, and electromagnetic interference and compliance, or EMI, EMC. And in all of this, simulation plays a very critical role. The second is on autonomous vehicles, which are years away to be seen on our roads, but obviously there are companies which are testing them out even today. In the case of autonomous vehicles, also there is a lot of reliance on simulation through sensors, target detection, environmental scanning, as well as environmental impact on sensor performance. Let us say, for example, there is water, snow, or soil on any one of the sensors. How is it going to impact the performance of autonomous vehicles? So with that, let me switch tracks and give you some idea about Simulia. Simulia is one of the brands within Dassault Systems, and Simulia focuses on realistic simulation, all that I have talked about in the context of electric vehicles till now. Simulia solutions are spread across multiple disciplines. So very briefly, on the structural side, we have Abacus. Many of you may be familiar with Abacus. This is a general purpose simulation software based on finite element analysis. And then we have multi-body simulation that is done using SIMPAC. The vehicle dynamic simulation that you saw was through SIMPAC. But SIMPAC not only does multi-body dynamics, but can also look at some of the noise and vibration workflows, such as gear whine and gear rattle analysis. Then there is durability or fatigue analysis, which is done using FE-Safe. FE-Safe can also work on fatigue of welds, as well as rubber components, such as engine mounts, for example. And then there is a vibroacoustic software called Wave 6, which uses a combination of finite element analysis, boundary element method, as well as statistical energy analysis to solve vibroacoustic problems. On electromagnetics, there are two products. One is CST Studio Suite, which is for high-frequency electromagnetics, and the other is called Opera, which is for low-frequency electromagnetics, typically for magnets and motors, which find applications in electric vehicles. On fluids, there are multiple products. There is PowerFlow and XFlow. Both of these are very powerful CFD solvers based on the Lattice-Boltzmann method, which makes PowerFlow and XFlow able to solve transient fluid flow problems. And then there is the 3D Experience Flow solution, which is based on the classical Navier-Stokes equations. On automation, there is EyeSight. You would have seen some videos in some of the videos, both Royal Enfield as well as the electric drive video, talking about multidisciplinary optimization or looking at design alternatives. And this is precisely where EyeSight comes into the picture. On optimization, there is Tosca, which is used for non-parametric optimization. If you're into 3D printing or additive manufacturing, you would know that, given a design space, you would be able to come up with the form, the geometry that you're interested in. This is called as functional generative design, and the technology behind that is topology optimization, which is what Tosca provides. EyeSight, as I said, is for parametric optimization, and this is where you look at design of experiments, what are called as design approximation models or meta models, and also stochastic analysis. If somebody wants to look at Six Sigma type of applications, look at what is the reliability and robustness of their products for standard performance, and that is where EyeSight comes into the picture. So I talked about the multi-scale and multi-physics nature of simulation, and this is important not only for electric vehicles, but also for new trends such as additive manufacturing, Internet of Things, drones, and now we are also looking at virtual human modeling. In Simulia, our aim is to connect all these different dots together, and what makes this possible is the use of the 3D Experience platform that I talked about earlier. Just a word about Dassault Systems, our parent company. Dassault Systems is a scientific company. We have more than 20,000 employees now. In India, we are spread across 6 cities and 3 R&D labs with more than 2,500 people. We have more than 200,000 customers across 12 industries. And we are long-term driven, which means that we not only focus on global trends such as electric vehicles and additive manufacturing, but we also drive and sometimes define these trends. And if you're more interested about this, I'll be able to share some details on this. And this is what I just lastly wanted to share. To stay connected with Simulia, feel free to look at what is called as the Simulia Learning Community, or SLC. It's very easy to remember. It's 3ds.com/SLC. Here you'll be able to download the student edition of some of our software applications. You'll be able to look at tips and tricks, attend some of the seminars that we do regularly. There is also a blog that is available, 3ds.com/simulate, where we talk about some of our interesting applications that customers are using Simulia for. And if there is anything, feel free to reach out to me. I had mentioned my email address right at the start. It's bhavesh.kumar@3ds.com. So with that, I would like to close my session. As I said, I wanted to keep it short, but hopefully this has given an overview of what are the applications of simulation today in the automotive industry, and specifically why simulation is going to play a very critical role in electric vehicles, both from the point of view of battery design, electric drives, as well as the overall full vehicle characteristics as well.
Thank you, Bhavesh. I think it has given our participant a macro level view how they can learn the simulation and use its application into electric vehicle, specifically into the component designing, the electric vehicle battery designing, and the vehicle itself. So, guys, you can post your questions in the question section, which is in the right side of your platform, or you can click on the raise hand button, where we would be taking few questions on the live feed. So, I request all the participants to keep posting questions. Meanwhile, I would be picking the existing questions. So, Bhavesh, we have got questions around from the material to the product or to the function.
Okay.
I want to take first question from Ashish Mudgal regarding the simulation itself. That how does the simulation process change when you are doing it for material or molecular level, or you are doing it for a physical product, or you are taking it ahead and doing it for some logics like we do it for the electronic circuits, and how it changes when it is done for a whole product like a car where the functions are also considered as a parameter to simulate.
Sure, that is an excellent question, and it goes into the multi-scale part of what I was talking about. So, if you take at the molecular level, first of all, the computational method that is used at the molecular level is very different. If you are familiar with, say, finite element analysis, one thing you would realize is that it is based on the concept of continuum mechanics. Now, when you go into scales which are very small, like the scale of molecules, the scale of grain structures within some metals and so on, the assumption of continuum mechanics doesn't hold at all. So what happens is that we have to use techniques which are more suitable at that level. So there are some techniques like that which are available. So now what we do is we can take the molecular level analysis and subject it to certain tests. For example, how does the battery behave when, or the materials inside the battery behave when the material inside them changes, right? Is that going to change the electrical impact in the battery? So once we get this information, what we have to do is we have to take the results at this micro level or molecular level and to pitch them into a level that we are more interested in, which is the level of batteries, right? Now, at the batteries, we are obviously interested in areas like performance. How fast is the battery going to charge? How fast is it going to discharge? If I double the load on the battery, how is it going to impact the discharge cycle and things like that. So what we have to do is we have to somehow take the results of our molecular analysis and apply them onto our battery model. The way we do that is using scale bridging methods. Okay, so there are methods available that will take the results of one scale and apply it at another scale. And maybe I can share some information. We have some write-ups that are available, which talks about what are different scale bridging methods and how they are applicable and things like that. But essentially, this is what a multi-scale modeling and simulation looks like. Each scale would use a different technology, but ultimately we want to bring it together and take a common decision, which is whether this battery is good enough or whether should I be looking at some changes to the design.
Got it. Akshay Navalka has asked that how you mentioned about the Six Sigma principles and how these are used in the simulation of the automotive components.
Great. So let me give you an example of that. Okay, so let's take the case of a rubber mount. Right now, as you know, there are engine mounts that are used to isolate vibrations from the engine. Now, what would happen is that uh, when you design an engine mount, you would be designing that for a specific frequency or a range of frequencies to be isolated. Now, you could do this using simulation. Now, what happens is that there would be hundreds of thousands of mounts that would be manufactured, right? Now, every time you manufacture a mount, there is going to be some variation. The variation can come from manufacturing, like manufacturing tolerances. The variations can come from the batch of material that is being used. So what ultimately happens is that in terms of the fit itself, there is variation. So what you could do is you could define these variations as input to your optimization model. Okay. Some of you might have heard about the Monte Carlo simulation. Okay. What is Monte Carlo simulation is that it's a way for you to randomly look at a distribution, right? And figure out what would be the impact of this variation on your output. In this case, the input is the variability that can come due to physical properties, variability that can come due to manufacturing, and so on. And the output is the performance spread. Okay. So what would be the impact on performance due to this? So Six Sigma is not necessarily the ultimate goal. Okay. It could tell you what kind of variability you are seeing. In technical terms, we call it as reliability and robustness. Okay. Reliability is more in terms of ensuring that the product performs as designed, and robustness is to ensure that the product performs even when there are certain things that would change in the product specifications, right? So these are types of things that you could use simulation along with optimization to ensure that the product quality is something that remains acceptable.
Sure. So that I think touched most on the Six Sigma for the simulation application. We are getting more question on autonomous vehicle. Nayan had asked that how and which software we can use for autonomous application in the automobile.
So, in the case of autonomous applications, there are, it would depend on what kind of simulation or what kind of requirements we are looking at, right? One of the areas, obviously, for autonomous applications is the very complex algorithms that would be there to ensure that the vehicle is, when it is autonomously driven, it is able to look at, it is able to take decisions, when there are barriers, when there is something on the road, for example, the passengers coming here and there and pedestrians coming here and there. And so that is one part of it. But at the same time, some of what I am specifically talking about is in terms of sensors, because in order for an autonomous vehicle to be able to take these decisions, it also needs sensors which are tracking all these inputs. These could be optical sensors, acoustic sensors, infrared sensors, and things like that. Okay. Now assume that an autonomous vehicle is on the road and it starts raining. So what would happen? So one is, so yes, there is an algorithm that will ensure that when it rains, the autonomous vehicle is still able to take certain decisions. But at the same time, what happens to the performance of the sensor itself because it is raining? Or you're going to take that autonomous vehicle and driving it on a road at a 45-degree outside temperature. With that increase in temperature, will the sensor performance be still the same, or will it start deteriorating, right? So what happens therefore is it's not just a single application that we look at, not just for autonomous vehicle, but it could be a connected vehicle, it could be an electric vehicle. Depending on the requirements, we tend to use different types of applications. So CST Studio Suite that I talked about, for example, it can be used to measure the performance of these sensors. But we have tools like PowerFlow, for example, which can do what is called a soiling and dirting analysis, which means that if the sensor is covered with some soil or dirt, then what would be the impact of that on the sensor performance? So it will be a combination of software, depending on the actual requirements.
So thanks for that detailed answer. So one question we are getting is on the battery. That what modeling challenges one face while simulating a battery? What are all the critical components and how one is able to manage the thermal condition as well as able to predict the aging through the simulation?
Okay, so if you're still able to see my screen, it is better that I just show the slide. Are you able to see this?
Yep. Yep.
So, uh, see, battery simulation, as you could see from here, is not a single simulation again. Depending on what you're interested in, we can start at a different level. Now, most of the time, what a company here would do is they will not be looking at molecular level modeling and chemical modeling, because the type of batteries that would be available to them, they would already know about the battery and its specifications, right? Unless the company is actually into materials research, which could be companies like DuPont, for example, who might be doing something similar. But most automotive companies, whether they're OEMs, startups, or suppliers, what they would have is access to certain types of batteries. So what they need to do, first of all, is to understand how appropriate or effective that battery is for their requirements. And that is where you see at the cell level the types of analysis that get performed, whether it is in terms of aging, thermal, electrical, and so on. If you notice, aging, thermal, electrical is in what is called as the 1D space, which means that people don't necessarily do detailed 3D modeling of those batteries, because 3D modeling is only required when you want to use that information in, let us say, a full vehicle model, like what you see at the bottom, right? Mechanical, thermal, and fluid. But when all you're interested in is to figure out what is the battery performance, either as a cell or as a pack, then there are very fast and very efficient battery management system modules that are available, which can tell you, how the battery is going to perform given the inputs. The inputs could be the type of the battery, the type of load that you're putting on the battery, and things like that. And these tend to become these tend to be very fast simulations. And one of the advantages of doing that is, if you want to optimize battery performance, you could do that quite quickly. So let's say, for example, you're looking at a battery pack or a battery module of 3x4 array, and instead of that you want to go for a 4x5 array, which means that the battery sizes will become different. Will this really give you the right battery performance, or will you have to change the configuration maybe a little differently? So these types of questions are easily answered when you go into this battery management system modules. So hope this sort of answers the question you're looking at.
Got it. Few questions on the training and getting into the simulations. So first, I would ask from the startup angle, how can startups can access the Simulia suite and how they can accelerate the development of the products?
That's a very good question. So, I actually wanted to share a couple of slides on how startups are using simulation. I was not able to do that because, I thought we will use this time for Q&A. But one thing I can definitely do after the call, maybe work with you, Vijay, to share some of this information on how startups are using simulation. But one thing that I can share with you is that we work very closely with startups. Today, if you look at the global startups in the EV space, pretty much all of them use Dassault System solution, whether it is in the form of modeling or simulation or even manufacturing, right? And the reason for that is quite clear. So what we found when we started talking to both startups as well as to traditional automotive OEMs is that there is a need that everybody is feeling to accelerate the time to market. Now, as we all know, the current traditional car that we have, IC engines, are there with 100 year of development cycle, right? Over the last 100 years, people, organizations, research institutions, they have put in so much effort, and there is so much that has gone into making the IC engine what it is today, and the cars what they are today. But obviously, we can't wait for another century for EVs to pick up. We are literally talking about months of time rather than years of time. And this is where startups are using simulation. And startups feel that they have an edge because they are able to start from scratch. Whereas the challenge that traditional OEMs sometimes face is because they need to get out of the mindset of developing the traditional vehicles and start thinking more like startups, right? So I think startups are more well poised to use simulation technologies. One of the things we are doing for startups also is to come up with programs that can help startups to pick up simulation faster. One thing that I can share is in terms of cloud. If startups are more open to using cloud than traditional OEMs, because traditional OEMs are invested in hardware infrastructure, right? So I can share more details definitely. If any of you are working with startups, then feel free to reach out to me or through Vijay, and I can definitely share more information. We'll be more than happy to work with you as well.
Sure, we will share that information across our participant as well in their benefit. One more question on the modeling and simulation before we jump to the students learning and getting into the EV space. People have asked that how the real-time vehicle dynamics modeling works when the various forces are acting on the vehicle. Can we simulate it on the real time?
That's a very good question again, and the answer is yes, we could. If let me just show you another slide, the one that I showed for full vehicle. Okay. So if you see the analysis, the animation that is going on at the top, which is on the vehicle dynamics side, this is done using SimPack. Okay. So SimPack is a multi-body dynamic simulation software. But one of the things that SimPack does is solve the multi-body dynamics equations using what is called as the relative coordinate system approach. Okay. So if you're into mechanical engineering and you have taken theory of machines or something similar where you're working on mechanisms, the way you build your equations and solve them, that is precisely the way SimPack works. Okay. And one of the advantages of that method is when your system becomes complex, like a full vehicle, SimPack will be able to solve it because the number of equations doesn't really increase that much. Okay. So this allows us to really go into a real-time analysis of vehicles. Now, how do you do that? Obviously, if you want to do a real-time analysis, so you have to look at a man-in-a-loop type of a method, right? So what we have is we will have the control box, which would sort of simulate the control systems which is inside the vehicle. And we have a setup where you as a driver, for example, you can sit on it, you can drive the vehicle, so it is sort of like the simulator that you see in some of the driving schools, right? The only difference is that along with the simulator is the control box of the vehicle itself. And whatever you do, let's say, for example, you take a left turn or you apply a brake. So that information now gets passed on to SimPack, and you will be able to see real-time changes that will happen to the force and motion characteristics there. So this is something that is used by companies like Daimler, Mercedes-Benz, Jaguar Land Rover, and so on, to do real-time analysis of their vehicle designs.
Awesome. One of the last questions which I'm picking from the questions before, as you post more questions. Many questions we have got around that. How can what you would advise to students to learn? Like what are the must learn things around the CFD or the simulation, which allows them to get into the simulation application to the EV industry?
Sure. So as you would have seen, if you had asked me to give this presentation about 5 years back, you would not have seen this much of multiphysics content. What you would have probably seen is a lot of finite element analysis, maybe a little bit of CFD and a little bit of electromagnetics. Today, what is happening is that the role that disciplines like CFD, electromagnetics play has also increased. If you're specifically looking at the automotive sector, I think you know that about 40 to 50% of the cost of the vehicle is in the electronic side. right? Which means that there is always going to be a demand in the near future, not always, but the near future, looking at the next 5 years or so, there will be a demand in terms of engineers who are able to make sense of all this electronics that goes into the vehicle, whether these are systems engineer, whether these are electromagnetic engineers, and more importantly, these are people who are able to look at functional and logical aspects, like the 1D modeling that I talked about, again called as system modeling, embedded systems and things like that. So there is that one big area, right? The second area that I could mention is in terms of fluid dynamics. Now, CFD is not a new field. Okay, CFD has been around for a number of years, but what is happening is that CFD is also being pushed more and more. Today, if you're looking at fuel efficiency, then one of the things that car companies need to do is to look at the aerodynamic drag. Now, in the past, what companies have done is to do a lot of wind tunnel studies to find out, how they can reduce the aerodynamic drag, and that is why cars have become sleeker over the years, right? If you look at the car model 10 years back and now, the reason why they are sleek is because they have done a lot of tests to reduce the aerodynamic drag and therefore make it more fuel efficient. But CFD will continue to play a lot of role because it's not just about flow, but also about thermal management. Okay, the same technology that tells you whether the aerodynamic drag is low or high is also the technology that is telling you whether your engine is heating up and whether you need a proper cooling system for your engine, right? And the third area is structures, which is always there. It has been around for a number of years. There are still a lot of opportunities that people can have on the structure side, which is finite element analysis. But what I would like to really encourage you people to do is to look at it from a multi-physics aspect. Okay, don't restrict yourself to a single technology or a single discipline. If you're able to learn how to combine these technologies together, then that would be great. Why? Because ultimately, if you look at a product, let us say an electric drive is an electric drive. Ultimately, you want that drive to work well. Now, what all technologies go into it, we have seen. But if you're able to sort of think along those lines and get into a multi-physics mode, then there is a lot of scope. Companies are always on the lookout for people who are able to go beyond these traditional disciplines and talk what we call as a system language, right? So I hope that helps. That gives you some perspective on what the industry itself is looking at.
Sure. I think engineers has got fair idea how they can get into this space while learning and not focusing on this a niche specific skill rather than going a ecosystem approach where they can adapt to many skills and apply many skills at a time. Which, as Bhavesh mentioned, even many companies are looking for such resources. Always, before we conclude this, one more thing I want to get more your comment on is that since you mentioned that there are communities like SLC where, yeah, people can learn the Dassault software suite. What else resources you think would be great, or what kind of projects which would be great for final year or passed out engineers to go through so that they are aware of the simulation technology before they even apply for the jobs?
Sure. So one, yes, I think let me just show you the Simulia learning community page. So if you see the Simulia learning community, even this will give you some idea. You can see that there are some technical topics such as material modeling and customization, that are a part of the Simulia learning community. One of the areas that almost all companies look at is in terms of material modeling. It with more use of plastics and rubber components, companies are really interested in how they can be characterized. The instrument panel of the car is made of plastics, and every company wants to ensure that it remains good, even after certain years of operations. That is one thing. I think so. There is a lot of content that you could look at the Simulia learning community. Do log in, and you can also reach out to the community if you have some questions or comments. This is a community that can give you some answers. In terms of projects, I would say that I think the projects could be in a few areas. One is in terms of really looking at what I would call as automation capabilities, right? Because even today there are a lot of workflows that can benefit from the right level of automation. This not only speeds up the process itself, but also makes it more efficient. The second aspect, something that you can add on the top of what you're currently doing in final year projects, is optimization. Okay, optimization, what I talked about in terms of statistical methods and so on. That is something that will give a little more insight into how companies think, because simulation is not about taking a design and finding out whether it will work or not. That is not what simulation is for. Simulation is for us to take a decision on arriving at the right design. And what helps us to do that is these types of optimization techniques. Okay, so if you are able to extend your, I would say, the simulation project from using techniques like optimization, then that is a lot more value that you add to your final year project as well.
Got it. And that's, I think, a lot of information for our participant to digest. You shared a very rich PPT, which has like a whole overview of the simulation processes, and I think our uh, participant are benefited from this information, and they are able to apply this skill set while looking out for jobs when they are graduated out of the college. With that, Bhavesh, I really want to take a moment and thank you again for agreeing to share your evening for the student community where which want to get into the EV ecosystem. I really appreciate your time and efforts in putting together the presentation and answering our all of the questions in the detail.
Sure. Thanks a lot, Vijay. Thanks a lot again for inviting me. It was really great to have this session with you all. I have put my email address in the slide if any of you would like to reach out to me for any further details or any questions that you have. And before I close, my very best wishes to you all. I hope that you will have a great year ahead. And that you will have a great career as well in the area of electric vehicles or in the area of your choice. So best wishes once again to all of you. And thanks, Vijay. It was an absolute pleasure to have this session.
Thank you, Bhavesh. We are very fortunate to have you in the session today. Thank you, participant, for your questions and your participation for the whole session. I appreciate it, and we would be sending the recording of the session once it is up. Thanks again. You can join the social launch to network with the other participant, uh, uh, and also you can put together your questions and email to the Bhavesh at mentioned email ID. With that, thanks a lot. Bye bye and take care.
Thank you.